In this section, we're going to do a quick overview of a few problems that you might encounter in probability. And this section is not in any way comprehensive on the topic of either probability or statistics. For that, I recommend that you take a proper course in statistics. But hopefully what you see here will whet your appetite for some better things to come. So let's take a look first at the idea of experimental probability. And what we're trying to do is use data that is already known to project or imagine something that is unknown. And so we first determine experimental probability by saying that P of E, which is the probability of some event. So E means event. And typically, when we're looking for probability, we have some particular feature or occurrence in mind. So we're looking for the number of occurrences, and that's of our target feature. And we want to divide that number of occurrences of our target divided by the total number of observations, which we sometimes will call the sample space. So let's take a look at an example. We have in a survey of 5,000 randomly selected Stanislaus County residents. Out of those, 2,067 reported their ethnicity as Hispanic. And if we want to find the probability that a randomly selected Stanislaus County resident is Hispanic, we will use this actual data. So what we are trying to do is use the actual data to get some information or projections of the entire population, which is over 200,000 residents. So we will do the calculation and we'll say that the probability that a randomly selected resident is Hispanic, or probability of Hispanic, is equal to the number of occurrences. So the target feature is that a person is Hispanic, and we have 2,067 of those, divided by the total number of observations, which is the 5,000 people that were surveyed. So this is a simple calculation. We can use the calculator, and we end up with 0.4134, or 4,134 10,000. So we're seeing that a little bit less than half, or 50% of the population which was surveyed, is self-reporting as Hispanic. Once we have this data, we'll use it to make a projection about the rest of the population. And so if 3,000 residents are randomly selected, and the implication is that these 3,000 residents are not necessarily from the original 5,000 that were in the sample, but any residents in the county. And so again, we're going to make a projection about the rest of the population, but we're trying to determine what is the probability that all three are Hispanic. So when we do this calculation, we realize that each of the three residents that are selected is considered to be an independent trial. And so the probability that all three people selected will be Hispanic will be the product of each probability. So for our purposes, we can use this experimental probability of 0.4134, and we can multiply it 3 times, that is, raise it to the 3rd power, and we end up with a rather surprising result, and that is that we end up with only 0.0706, which is approximately 7%. And this occurs because every time you have a fraction that's less than 1, when you multiply it by itself, that fraction becomes continually smaller. For example, if you take 1/2 and you square it, 1/2 times 1/2 becomes 1/4. And if you take 1/2 and cube it, it becomes 1/8. Next, let's move on to theoretical probability, which is defined as being the number of ways that an event could occur divided by the number of equally likely outcomes. And we see this in the rolling of a die. So when you think of a standard die, if we're asked, what is the probability of rolling a 6 with 1 die? Well, the number of total outcomes is 6 different numbers, 1 through 6, so we'll put that in the denominator. But there is only one way of rolling the 6, and so the probability is 1/6. If we were, for example, to try to find the probability of getting an even number, we would say that there are 6 possible outcomes, so we put our 6 in the denominator, but there are 3 even numbers. There's 2, 4, and 6, and so the probability of getting an even number would be 3 divided by 6, which reduces down to a half. Let's look at the next example, which asks, what is the probability of rolling a 7 with 2 dice? And here our sample space becomes more complicated. For each of our 2 dice, so for die number 1, there are 6 different possibilities, the numbers 1 through 6, and the same for die number 2. But these 2 dice are considered independent because the roll of one doesn't affect the roll of the other, so we'll multiply the number of possibilities for a total of 36 possible outcomes, and that's going to be our denominator. Next, I want to determine the number of ways of obtaining a 7 with 2 dice. So I'm going to write the number values of the dice that combine to make a total of 7. This is not how many combinations there are, but the actual combination itself. So on die number 1, I could have a 1, and then on die number 2, I could have a 6. I could also have the combination 2, 5, and 3, 4. And I also have the combinations 4, 3, and 5, 2, and 6, 1. And certain combinations such as 1, 6, and 6, 1 may appear to be repetitions of each other, but they're actually not if I distinguish the first die and the second die. So I have a total of 6 combinations that will produce the number 7, and so I'm going to write that up here, and therefore what I'm seeing is that the probability of rolling a 7 is equal to 6 over 36, but that reduces down to 1/6.